Okay, so as usual, right? The This week's lecture is going to be on next week's lab, and next week you're doing this thing called pulse width modulation and dealing with block RAM. It sounds really boring, right? But it's basically what like a MP3 player or a video player is made of, and you just basically actually a pretty neat thing where you're basically forwarding the digital information and then converting it into analog information and then outputting that at the same time, which allows, these MP3, well, when I was a kid, right, way back in the 90s, right? Well, not even like maybe early 2000s even. Um, you're able to buy like an MP3 player for like $10 or something like that. It's like it's like a ridiculously cheap thing, right? Where most of the cost is actually the packaging and the memory that's actually storing the data. That's because, right, in order to play audio is actually a very simple thing, and we're going to see how simple it is, and then you can like write this algorithm into like 2-3 lines, and that's how I want to show it to you guys. And you'll do a lab on it next week. Okay. One important thing is that as you work on the labs this week, especially, right? One thing to notice to keep in your head when you're working with the Verilog or VHDL, in case you ever go work at Intel or something like that, that don't think about it. This is a thing that like a lot of programmer gets confused by, where in a lot of programs, the codes are executed one line at a time. C equals to D, D equals to this, E equals to that. It's like in sequence with each other. Okay. In hardware descriptive languages, right? That's what HDL stands for, right? Think about it as you programming what wires gets connected to which wire, right? Once those connections are made, those wires are permanently there, right? So whatever C equals to D is, right, is going to be C equals to D all the time, no matter what, because they're physically connected to each other, okay? If C equals to D, if C is high or 5 volts, right, D is always going to be 5 volts. Even if you try to change it later, it's not going to allow you to do that, right? So just be a little aware as the codes get a little bit more complicated. Think about these. What you're doing is you're hardwiring codes. Instead of doing it on the breadboard, you're connecting them through this little FPGA thing, a array of things where you're just connecting wires that crosses each other like that. Okay, and that's why we went through that whole process to tell you what FPGAs are. Okay, so this week's lab we're going to do is you're going to be like, you know, using flip-flops to store information and then maybe transmit them through like a serial link or a parallel link, right? And remember, the idea is that there's oftentimes resources that are very limited, right? So let's say you have limited number of CPU cores, right? But then the CPU core wants to access multiple memory banks, right? So what you do is you have a multiplexer. Unfortunately, this thing goes the other way, where, right, you have a little trapezoid like this, where this multiplexer is able to access multiple places, and then with a little selector key here, you're able to actually select what memory banks to read out. And then the demultiplexer is the other way, where you have one input and then you're going to different output, and you can actually and you're going to build that in the lab next this week. Okay, and this gives rise to all these technology you guys are using, the universal serial bus. How does the data in your computer gets converted into these serial ports and stuff like that, right? And now we're going to go one step further, is we're going to think about how does the digital information inside your computer gets converted back to analog information, right? Because when I'm talking to you, I'm making sound waves, right? That's hitting your eardrums, right? That's vibrating a little bone inside your ear, right? And that has little hairs on it, and that little hair has a little nerve ending that sends information to your brain that tells you what frequency of sound you're hearing, right? So everything that happens in real life is actually analog, right? But all the processing happens in digital, right? Because digitals are just easier to deal with, so you don't have to worry about noise and stuff like that. Okay. So what I'm going to do this time is, let's say you have some digital system. We're going to do a digital to analog conversion where we're going to basically play some music from a computer that's going to be programmed into your memory banks inside your FPGA, so that it can actually just place, like 20 sec, well, not even 20 seconds take a long time, like 10 seconds of sound. Okay, but you can imagine you can, make this bigger and bigger and bigger as you want. Okay, and the first thing we're going to do, the first technique we're going to use is this thing called pulse width modulation. Okay, and that's why this lecture is called that. And most MP3 players, especially the cheaper ones, and even the ones that you're running in your computer, I don't know, people still use that, like Easy Folder MP3 player. There are players, right? And you're wondering, right? Why is, I'm playing this, audio stream that's, has like, 100 kilobits of fidelity, has, it's very high quality audio, right? How is it like not using any my processor to do this, right? Right? And this is done through this method called pulse width modulation. Okay? And we're going to see how simple the instruction set is. Okay? Same thing with video players. Okay? When you're playing videos, as opposed to a single channel that's pulsing up and down, for each of the dots in your screen, you're basically just sending that signal in parallel, and it takes almost, well, the more pixels you have, each pixel is basically, you can think about it as like one sound wave you're playing. Okay? And then of course the more pixel you have, the more, even though this method is very simple, right, it still takes a little bit of processor time in order to do that. So when you start playing, 4K video and stuff like that, it may take up like a couple of processors in your computer to do that. Okay? So to introduce this, we already kind of did when we looked at the 555 timer clock chips. You may think of like, what the hell does that have to do with pulse width modulation? We were introduced to this idea called duty cycle, right? Okay. Duty cycle basically tells you what fraction, right, the clock is at the high mode as opposed to low, right? Because you can imagine making a clock that has a 25% duty cycle, where most of the time is actually off, right? This may save power actually, right? Because when you have a clock, all you care about is that, oh, when the circuit see this up pulse or see this down pulse, right? Right. Remember, doing both allows you to do a DDR RAM type of thing, right? So that's all you care about. Okay. But you can, run your timer, your clock at 75% duty cycle, right? Where right now, right, this 75% duty cycle is outputting a lot more high, a lot longer, right? Right? And then if you imagine, right, whatever this, circuit is connected to, right, it has some resistor to ground, right? When the pulse is high, you're going to be running current through this. When the pulse is low, you basically have no current, right? You're not using power at all. Okay? So you can imagine that, right, when you have higher duty cycle, you're outputting more power, right? Duty cycle is approximately power output, okay? But just as a digital version instead, okay? Let's not call it digital. As opposed to like having a pulse that goes, up and down, it can be just a fraction of time is up, okay? Okay. So, and that's the idea of pulse width modulation, where you can control the amount of time the power is being sent out of your circuit into whatever device. In the case next week is going to be just like a computer speaker or your headphones or whatever you want. Okay. So for a speaker, you can model it pretty closely as a resistor, right? So if you have a resistor, the power outputting through a resistor is the current running through that resistor times the voltage drop across that resistor, right? And you can, of course, use Ohm's law to replace the current with V over R, and therefore the power output is actually proportional to the voltage square. Okay? So when you have digital information inside your computer, okay, usually it's going to be compressed into an MP3 file, so there's some compression involved, but you can actually print out the raw file. Okay, so you can actually print out these raw files. Okay, so this is a little Python code that you don't have to worry about. You're not going to be, asked to do any of this stuff. Okay, but I just want to show you guys what it looks like, and the code is actually pretty simple, where I converted it a little sound file into its raw format, and what it means for it to be in raw format is that it actually tells you how high the voltages are. Well, how high the digital level is. It's not necessarily voltage, right? And how low it goes. So you may have seen something like this on like a TV show or on a player on your computer, where it's like when you're playing something, it just does this pulsing thing. You ever seen that? Yeah. Okay. So this is sound waves, right? Actually, if I zoom in a little bit, it'll look a little more clear, right? These are sound waves that has multiple frequencies in it, right? Superimposed on top of each other. Okay, it's complicated, right? Blech. Right. And then if you want, you can do a Fourier transform on this and pick out all the frequencies if you want, but we're not going to do that. Because all we care about is that while here, right, we have some high frequency changes, right, that are up and down, up and down, up and down, right? So whatever the speaker has to do, right, whatever the sound output has to do, it just has to have some high amount of output here and some lower amount of output here, and probably pretty quiet here, right? It's just a little bit of noise down here. Okay? Okay. In fact, this is a 8-bit audio file, and the reason it's 8-bit is because the range here goes from 0 to 255, right? So it's 2 to the 8 is 256, so you can store information from 0 to 255 on an 8-bit 8 bits of data, what do you call it? 8 bits of information, okay? And the specific audio files we're going to be dealing with actually are 8 kilohertz audio files. So that means the voltage changes every 1/8 thousandths of a second. It's not that great. You're going to hear that it kind of sucks. So generally, if you want like what you see on CD play, well, not CD. People still have CD players, or whatever the MP3 format is, right? Usually it's about 40 kilohertz. Okay. Okay. And the one reason for that is actually stay away from the human hearing range, because what's gonna happen is that this 8 kilohertz, you actually can still pick it out because it's within our hearing range, right? Because our hearing range goes up to 20 kilohertz. But this is good enough for us to just play around with the FPGA sign. Okay. So the voltage range is from 0 to 255, right? And each data point is going to be 1/8,000, meaning it's going to be about 1.25, well, it's exactly 1.25 milliseconds, okay? So that voltage changes every 1.25 milliseconds, okay? All right, so that's what a little audio file looks like in this raw format, okay? So how does pulse width modulation help you with this, okay? So what we're going to do is I'm going to describe a simple pulse width modulation, and then you're going to write this in your homework yourself, okay? So you have some, let's say, let's ignore that part. That's just kind of the clock. Okay, let's say you have some simple sine wave, okay? Okay, let's just keep it simple, right? Okay. What pulse width modulation does is that whatever the pulse, or also known as the duty cycle, right? The pulse width is going to be proportional to the height of your sine wave. Okay, hopefully you guys see that. So let's start here, right? When it's at, so the vertical axis here starts at 0 down here, right? So in this particular clock, let's say this number is somewhere in the middle, right? So this is going to have a pulse that's, maybe about half the width, okay? But then when the sine wave peak gets higher, right? This is a larger number, right? This pulse gets wider. You can see that, right? Whatever this width is proportional to the height, right? Okay. So then it gets smaller again, smaller, and smaller, and then even smaller until it almost reaches 0, right? So there's almost no width here, okay? And then it gets bigger and bigger and bigger, okay? Think about like the area under this graph as being equal to, whatever the height of this sine wave is, okay? The reason we're doing this is that, right, instead of trying to output the sine wave, all we have to do is output basically low and high, or 0 to 3.3 volts or 5 volts, whatever you want to do. In this, so you don't actually have to convert anything to analog in reality. Your pulse width is proportional to your digital value. Okay? And we'll see how simple, well, I'm going to show you the other one. But I'm going to have you guys write the simple version of it. So you're going to insert your code here in your homework. Okay? It'll have instruction on how to write this little module and how to initialize it and do all that stuff. So make sure you do your homework before next Monday, because otherwise you have to do it in the lab anyway, right? So, okay. So let's talk about, let's look at let's look at this algorithm just a little bit longer, okay? Okay. So what's happening here is that, right, whatever the output is, probably a speaker in this case, since we're dealing with sound, right? The width of this, right, basically the area of this tells you how much power you're sending out to the speaker. Okay? Right? A little bit of power, more power, little less, even less, almost 0, and then more, right? And that's representing the sine wave, right? So the same thing's happening, right? Where you have a little bit, great, decreasing at the minimum, okay, and then increasing again, okay? Well, you notice that, all of these numbers has to be positive, right? Because we can't have a negative pulse width. Because what happens is that if you pulse a negative, right, it'll still send out power, right? Which will give you so it can actually only represent positive values. Okay. So this is called the simple pulse width modulation because, right, it's what you would think about if you're the first time you're doing this. Okay. There is a drawback to this, right? You notice that, right, the pulses is happening right away, but then the whole thing is quiet for a while, and then it's pulsing again and it's quiet, pulsing again and it's quiet. So it's sending up, modest amount of power when it's up and no power at all when it's down. Okay. What I'm going to show you and actually give you the code to write, so you don't have to write the code yourself. I'm going to show you guys this thing called sigma delta pulse width modulation algorithm. Okay. So there's a slight difference between the two. Okay. So let's say you want your pulse power to go up like this, and then larger part here and a smaller part here, right? As opposed to just making it like this, right, where you have a pulse, right? You space out the pulse so that they're smaller, okay? So the pulses just kind of goes up and down, up and down, up and down, where the total area of this still adds up to this, okay? Right? With the big pulse, with where the sine wave is bigger, right? You pulse very quickly, right? At every clock cycle. So the area of this still equals to this. So you're still sending out the same amount of power, okay? But as opposed to just sending it all at once and then nothing, right? You're spreading that out throughout the entire clock cycle. So you're pulsing, up and down, up and down. And how frequent you pulse determines how much power you send out. Okay. All right. I'm going to show you how this little algorithm works, okay? Even with a little example. You can see how short the code is. It's literally 2 lines. Okay? So that's why your MP3 player, basically the processor takes no power whatsoever. Okay? Because all it's doing is actually counting some numbers, and that's it. And that's why this lab follows your counter lab, which is what you're doing this week. Okay, so this module, right, is called Sigma Delta Pulse Width Modulation, blah, blah. Just you can name that whatever you want, but hopefully you guys do that too so that I'm not confused on what you're trying to do, right? Here, in order for you to pulse with the clock, you need the clock input, right? In order for you to know how big the input and how small the input is, right? You need some input, right? We're going to call that xn, basically, the value of the sine wave. Okay, so let's go over here, right? Basically, xn, right, is whatever value of the sine wave is, right? Okay, and it goes from 0. In this case, 255 is the biggest, right? Okay. And then the only output you need is to tell the thing whether to pulse or not. Okay. I'm going to draw this on the side here, right? So in this case, right, let's do the pulses in red, right? Up here you have the sine wave is very large, so you pulse a lot. Down here you have a very small, you have a small value of your sine wave, so you pulse very little. Up here you have very large pulses again, right? And then in between you have the in-between stuff, right? Hopefully this is helpful at all for this illustration, right? So you have very shallow amount of pulses here, okay? The number of slashes indicates how many times you're pulsing up and down, how frequent you're pulsing up and down. So the more frequent you pulse, the more power you're sending out. You're basically sending out that power a little dribble at a time, okay? Okay. So let's see how this works, okay? So that's how this function just has 3 things, okay? Okay. Right? First of all, in order for us to store, what we're going to do is we're going to count up, right, from 0, not to just 255, but 255 plus 255. Okay? We may have to do that, okay? And that's why we have a little registry, right? Instead of 8 bits, we're going to have 9 bits, right? Because 9 bits allows us to store up to 510, right? 2 to the 9. Okay? I'm going to call that sigma. May not be the best name, actually, right? Okay. Right? And then whenever the clock pulses, right, it's going to start something. What's going to start is we're going to make sigma, which starts at 0. We're going to make it whatever it was up to the 8th bit, right? Not the 9th one, plus whatever xn is. Okay? All right? I'm going to say, what? What the hell? Okay? Whenever the 9th bit of sigma is 1, we make a pulse out. Okay? This is very confusing. This should not make any sense right now. Okay? And hopefully it doesn't. If it does, then you're a lot better than me then at this. Okay? Okay. So the way I do, figure this out, I say, okay, let's do some examples, okay? Let's say xn is the maximum value, right? When xn is the maximum value, you're at this peak right here, right? So that's where you want basically the pulse to be pulsing all the time, right? Right? In fact, if you actually draw this, it'll just look like this for the whole cycle, right? It'll just be high, right? That's when it's sending out the maximum amount of power, right? No? Good? Bad? Somewhere between the two, right? Okay. So hopefully, right, if xn is 255, we're going to keep our PWM out high all the time, okay? And you're going to see that it's not, which is okay, but it's going to be 1/256 of the period of the cycle, okay? So in cycle number 1, so I'm just kind of looping through this positive edge over and over and over again, okay? First cycle, right? Sigma is 0. I'm going to write this in decimal, but I'm also going to convert this to binary, okay? And this is going to, and this column here is going to determine whether or not the pulsar is going to have a high output or not, okay? And then I'm going to convert this, so the 9-bit sigma and the 8-bit sigma, I'm going to line them up with each other so that we can actually kind of play around with the numbers, okay? All right, so let's just do the conversion, right? Sigma is 0. Of course, the 9-bit sigma is actually 0, 0, 0, 0, 0, 0, 0, 0, right? 9 zeros, right? 0 in decimal means it's 0 in binary also, okay? If you take, right, let's just ignore this part for now. This will make more sense in the next cycle, okay? Right, so let's write in those zeros, okay? I probably should have typed it in, but I think my whatever software I wrote it in just removed those zeros for me because they were all zeros, okay? Okay, right? The 8-bit version of that is just this number without this 9th bit, right? I just removed this, right? That's the same number, okay? All right, so in decimal, that's actually, right, 0 still. Okay, 0 is equal to 0. So boring so far. But next time the pulse, the clock go up to its positive edge again, right? What's going to happen is that xn is this constant number in here, right? 255 all the time, right? Every time the clock goes high, we're going to have to add 255 to this number, right? Well, currently this number, right, is 0, 0, 0, 0, well, 0, okay, all right? Right, 0 plus 255, and I'm going to change that over, shift that over to sigma itself. So I'm going to replace 0 with 255, right? Because 0 plus 255 is 255, okay? So that means in decimal, right, the number I want to write into this little registry is 255, right? In 9-bit, right, that number is 0111111, right? Because basically this is 255, right? This will give you the 256 value, right? Okay, so we haven't got over 256 yet, okay? Well, actually, you know, in this case, if we're just taking this bit right here, actually we should just call this sigma 8. Okay, I think this was not a divider, it was just like an OR, okay? Okay, well, in this case, sigma 8, right, sigma 8, which is the 9th bit, right, is still 0, okay, so nothing interesting happens, right? The 8-bit version of sigma, right, is that same number, but then I just removed the 9th bit, right? But now, right, sigma is now 255, okay? So we're gonna have to wait till the next cycle that rolls around, okay? Okay, next cycle rolls around, what happened is that, right, the number we're adding, right, is 255 here still. This number is now what? Before, in the beginning of cycle number 2. What's this number? 255, right? Yeah. And now when you add those two numbers up together, you get 510 instead. Okay? The 9-bit version of 510 is just all ones with a 0 at the end because, right, this is the even number, right? So that has to have a 0 at the end. Okay. Now, if we look at this spot here, right, now it's a 1. Okay? Right? And notice that the last line down here is always, right? Remember, these are wires that you're connecting, right? Right? Whatever sigma A is always going to be the same as whatever the pulse PWM out is, right? So that means this is the same, right, all the time. PWM out. Okay? So that means it's going to make our first pulse to be high in this cycle. Okay? Okay. So PWM went high. Okay. Once again, I'm going to crop the last 8 numbers, right? So now you have, right, these 8, the 8-bit version of sigma, right? If you compute all this, the number is actually 254 instead. Okay. Right. The reason I'm doing this is that, right, this number is actually what's going into the computation here, right? Right? This number determines whether or not the pulse is high or low. Okay? All right. Let's see what happens next cycle. We're going to do this a couple more times. Sorry if you're falling asleep. Okay? Well, next cycle goes around, right? Xn is still 255, right? It's just stuck there, right? 255 plus 254, right? Instead of 510, it's 509. Okay? The binary version of that is the same thing, but then the zero is just shifted over one. Okay? You start to see maybe like shift registry work here, right? It's the same idea, actually. Okay? You're just shifting this zero over and over and over again. Okay? Okay? Okay, so, right, in this case, right, the 9th bit here, sorry, the 8th bit, right, is still 1, right? So the pulse width modulation output is still high, right? Whatever you're sending to your speaker is still high. Okay, you're still sending power to your speaker. Okay, once again, you crop this off. When you crop this off, you get this number, and now it's 253 instead. Okay, do the little binary computation. Okay, you add, what do you add to this next cycle? 255, yeah, right? Every cycle you add 255, right? When you add 255, you get 508. You get a pulse high still, because any number that's bigger than 255, you're going to pulse high, right? Because whether or not you pulse high or low is just determined by this 8th. Let's call this the highest, most significant bit up here, right? Okay. And you do this, right? And the next time it goes around, now the value you get by cropping off the last bit here, right? It's 252. And then and this is going to happen to 255 out of the 256 cycles. Okay, until basically this number gets to 0. Right? You start counting from 255, you get to 0. When you get to 0, you don't pulse high anymore. Okay? So, in order for this to happen, right, the number of clock cycle, right, within each sample, so let's say we're sampling here, right, this x is one sample point, right, let's say that x is equal to 255 here. The number of sampling has to be at least the number of bits, right? Has to represent at least the highest number, right? So the number of what we're going to call pulse width modulation clock cycles, okay, has to equal to, in this case, it's going to be 2 to the 8 minus, well, 2 to the 8, in other words, 256 for 8 bits, right? Oops. But if you're doing 64 bits, then it'll be 2 to the 64, right? Okay. Okay. That's just one sampling of your that's just like one dot in your audio file. Okay. Okay. Should we do another example, just to make sure this is not crazy? Let's do this this next example kind of quickly. Okay. Maybe we don't have to do that. Okay. So let's say xn was 127 instead. You know, basically half the maximum amount. Okay. Same thing happened on the first cycle where you just get zeros everywhere. The second time the clock rolls around, right, this number gets converted, right? Okay. And since xn is 127, 127 plus 127 is not bigger than 255, right? So well, it's 254. I just wrote it up here, right? So you still have a 0 out here. So you don't pulse high, right? Remember last time, by the time we get to this point, we already pulse high because the number we got back was bigger than 255, right? Okay. But what's going to happen is that when 254 plus 127, that's going to be bigger than 255, right? So that's where you get to 381, okay? And that's when the first time the output actually pulse high, okay? Right? But what's happening is that basically every time you go through this, you're removing this first digit here. by removing that first digit, you're subtracting 255 from the number. But actually 256 from the number, right? Okay. Right. So now you're at 125. 125 plus 127, right, is 252. So now the thing pulls low. Okay. So you get this high, low, high, low, high, low. So you're going to have high, low every other cycle. Okay. That means when the input is only 127, right, you're going to have a high, low, high, low, high, low. So what's the duty cycle on that in that language? It's 50%, right? Okay, so you're sending out 50% power out to your speaker now, right? Where up here, you're sending 255 out of 256, whatever that fraction is, right? Power out to your speaker, okay? Okay, right? This algorithm makes sense? So this is the more complicated one. That's why I'm not making you guys write it, okay? What you have to do in your homework is to write the simple one. You're gonna have to write the simple pulse width modulation as opposed to going up and down all the time. All I want you to do is pulse what fraction. What fraction do you want the pulse to be high, right? Okay. And it turns out to be a little simple calculation, right, on paper, but then when you have to convert it to Verilog, right, this is where the hard coding involves. You're gonna have to deal with a counter, right? And then every time the clock pulses, you have to add something to that counter. And then you have to say, oh, should I be high? Should the pulse PW underscore out, should that be high or low? Just make that check over and over and over again, okay? And I look forward to seeing the various versions of this, okay? Okay, okay, okay. So let's walk through at least what the inputs are the same with the sigma delta where, right, you have some clock, right? And this clock, right, has to be whatever the audio frequency is. In the case in our lab is 4 kilohertz times basically 2 to the number of bits, okay, right? Because, right, whatever the clock for the pulse width modulation is, you have to be able to go up and down 256 times per audio clock cycle. The audio clock cycle is 1 point, right? Let's go down here, right? Right? These point changes at 8,000 times per second, right? So 8,000 times per second, and inside each of those 1/8,000th of a second, you're going up and down up to 256 times per second, okay? And then if you're doing like CD qualities or something like that, it'll be like 42,000, right? With, let's say, 32-bit audios, right? So it's gonna be 2 to the 42, sorry, 42,000 times 42 kilohertz. So don't write this down because this is not relevant. So this is like CD quality stuff, right? And 2 to the 32. So that's how fast your clock has to be in order to do that, okay? And these are within the realms of what we do with our, just consumer electronics. Okay. All right. Let's go back to what these inputs are, right? So this clock in, right, has to be 250 times faster than the audio clock. Okay. In the case of 8 bits. Okay. If it's 16 bits, then it has to be 2 to the 16 times faster, right? Okay. Okay. Xin, of course, is the binary voltage values, right? Whatever it is, 255, 127, 0, whatever it is. Okay, so that gets set. Okay, and PWM out, right? That's the pulse, whether the pulse should be high or low, right? That's the output, right? That's basically going to be what's sending power out to your speaker. Okay, okay, because eventually this will just connect to some port through your FPGA to a speaker. Making sound. Okay, it's probably not the right drawing. Okay. Any questions about this algorithm? It's very simple, but it's a little hard to it tests you how well you understand. Oh, you're just connecting wires together. That's why this little lab is kind of fun, okay? As opposed to just clocks, flip-flops, and counters and shift registry. This is an application that just requires you to understand how you're connecting the wires together, and that makes sound. Okay, what time we got here? Okay, we got another 10 minutes. Okay, okay. So let's talk a little bit more about the FPGA, okay? And how is this data going to be stored on your FPGA? Okay, so let's say you have an MP3 player, back when people still have MP3 players, or you just call it the memory banks on your phone, okay, whatever. Sorry, you don't have to call it MP3 player. Okay, so you can put these these sound data on maybe like a separate storage device, like an SD card or something like that, or just internal to your device. So your FPGA has the same capabilities, the ones you have right here, but it's very limited, okay, because it's not really designed to store information, right? Okay, so if you actually go look up the spec sheet for for our FPGA, which is the XC7A37, sorry, 35T, right? It has these things called block RAM. Okay, okay. So each block RAM is 36 kilobits. I'm gonna write the bits out. Okay, so don't mix it up with bytes. Okay, and we have 50 of them inside this device. Okay. In fact, when you do this lab, what you're gonna start seeing is that when you program the FPGA with all these block RAM in there, it's gonna take up a lot of space inside FPGA. So there's gonna be a lot of wires being connected inside FPGA. Okay, and that's what majority of the implementation time is gonna be, is to connecting all those wires together. Okay, of course you don't have to do this yourself, right? You just tell the computer to do it. Okay, aren't you glad you don't have to do this? You know, this will be like, I don't know, like a million wires, something like that, right? Okay. You can actually physically see this, and I think the lab kind of like nudge you to say, oh, go look at the implementation design, and you're gonna see these block RAMs being used up. The reason they are called block RAM is because they comes in blocks. Okay. Okay. Each block RAM has 56,000 bits of information that can be held in it. Okay, the reason it's called block RAM is because if you use one bit of it, that entire block RAM is going to be used up. Okay. Okay. So if you're loading up 36,001 bits of information, this is going to take 2 blocks, right? Because of this one extra bit. Okay. Okay. And so on like that. Okay. But since we have 50 of them, we don't really care. Okay. And in the homework, you can actually calculate how much information you can actually store. Okay. Okay. And this is where we're going to store these raw audio file. Okay. So on Canvas, I uploaded a bunch of raw audio files, so you can use it. I think I can put them on the thumb drive there for the computers without internet access, right? Okay. So so you have access to these audio files, and each of these audio files will just play like 3-4 seconds of stuff, right? And you just have to tell me what they say. Okay. The first one I'll tell you is just someone counting 1, 2, 3. Okay. All right. So if you don't hear 1, 2, 3 on your first file, then something went wrong. Okay. Okay. So how do we do this in Verilog? How do we physically program our FPGA to store all this information using these block RAM? Okay. Fortunately, Verilog, well, AMD or Xilinx, which is the predecessor before AMD bought them, was smart enough that, oh, you're gonna do this all the time, right? Why don't we just write you a function that does that? Okay. And this function is called rememh. Okay. Okay. The reason it's called H is because all this data file has to be in hexadecimal, actually. Don't ask me why it's hexadecimal, but that's the way they wrote it. Okay. Okay. So In order for you to load this stuff, okay, what you need to do is you have to have a memory bank, right, aka a registry, right, that is going to be big enough to hold all that information, okay? And this is where this gets declared up here. So this registry of 7:0, which is how many bits? 8 bits, right? Because our audio file is 8 bits. And it has we'll call it memory, and it has some size that's, memory size -1, meaning because, as just like up here, right, the memory size, you always subtract 1 because you start counting from 0. Memory size -1, colon 1, okay? Sorry, colon 0, okay? And then what happened is that you're telling the FPGA, before you do anything else, okay, do this first, okay? And that's what this initial begin is going to create, okay? Before you do anything else, do this, because if you don't read in the memory, the file, right, then you can't, there's nothing to connect to, okay? So what's going to happen is that you're going to do this first, okay? And it's going to just, read memh and then the file name and then put it in memory, okay? By memory, I mean this memory variable, right? You can call this Bob, right? And then you have to replace this with Bob if you want, okay? Okay. Okay. And we'll also introduce this idea called local params, okay, which is a nice little thing where you can, this mem size thing, right, is now whenever you say mem size, it'll just replace that number, replace that variable with 19783, okay? So you don't have to like remember what that number is all the time, and then if you type, because if you type 19782, your code's not going to work because you're missing one bit of your information, okay? Okay, so actually it's 1 byte because it's 8 bits, okay? All right. Okay, any questions about this? You can also read this out in binary format. There's also memb, but that's for like smaller files, okay? Okay. In order for the FPGA to access these memory, okay, it has to know where it is, okay? So I'm going to do this little drawing once again. I probably should have planned ahead and made it ahead of time, but let's say my sound wave is this, okay, whatever this is, okay, okay, and then this is a high 8 kilohertz clock, right? Okay, so this address refers to basically the numbers here, okay, okay, at 0 second, right, the audio is at some amplitude, right? The sound wave is at some amplitude. So it starts 0, 1, 2, 3, 4, 5. So these address, right, corresponds to these numbers here, okay? So remember memory, right, is this 7.7 colon memory, right? And let's say for now it's 19, what was the number again? 197, sorry? 19783, right? 82, right? Because it's -1, colon 0, right? So this 0 here corresponds to this bank, right? Right. This 1 corresponds to the next number, 2 corresponds to the next number, and so on until the end here. Let's say the end here is 19782, right? That's the last number here. Okay. Okay. The address corresponds to 1 point on your little sine wave graph, or your sound wave graph. Okay. So it's not a sine wave anymore, right? Although there are like superpositions of a bunch of sine waves, right? Okay. Okay. So this address, right, is counting this up, right? That means how fast should it be changing? Should it be changing the same rate as the pulse width modulation clock or a different clock? Different clock. Which one? How fast should it be if it's
same sample rate as the audio?
The audio rate, yeah. So, ooh, this didn't update. Is the internet up? Interesting. Because I changed this name to odd clock. Okay, so I'll do this right now. Okay, So yeah, so you want, since the audio file is 8 kilohertz, you want this memory address to change 8,000 times per second, right? Okay. In fact, in the notes, I thought I changed this to odd clock. Odd. I just changed the name of it, so it doesn't actually do anything. Okay. Odd. Okay. So I'll just show you the code how that happens, even though I wasn't supposed to, because I think this is part of the homework. Okay. So if you take a picture of this, then you've done one of the problems in the homework. Okay. Where, right, every time you have a slow clock, that's your audio clock, and then you have a fast clock, right? That's your PWM clock, right? Okay. And every time that happens, right, you want the address to increment by 1. Okay. Okay. What happens at the end here is that when the address reaches the mem size, which is the end of the file, right, it just resets it to 0. Okay. So that's all this is doing. Okay. So it's just counters, right? Counters being used to make these, to change the which part of the memory address you're looking at. Okay. 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 And this is where I wish this didn't update for some time. Okay. And it's not going to update now that I wrote on it also, right? So just to know that the slow clock is called the audio clock. Okay. Right. And that's the one that's at 8 kilohertz. Okay. So you need 2 different clocks. Okay. In order to do the pulse width modulation clock, let's call it that, right? You need this to be 8,000 times 256, right? And that way it can determine whether to pulse high or low, right? Which is going to be about 2 megahertz, okay? So it decides that about 2 million times per second, okay? Which is, you know, still pretty slow, okay? Pretty fast for our brain, but slow for a computer, okay? Okay. All right. Any questions about how to do pulse width modulation, how to read out the information, and how to get the information 8 bits at a time? Okay, because that's basically going to be your lab next week. Okay, and there's some speakers here so you can make some noise.